computational analytical methods done in mathematics done last year. Builds on engineering mathematics from year 1 last year, or from analytical methods when you've done your HNC, Ben, yeah? Alright? So there are 4 learning outcomes. Applying further integration techniques and numerical methods to evaluate functions. It's not right. Here we go again. Learning outcome 2. Form and solve first order ODEs, ordinary differential equations, and second order ODEs. Evaluate the use of 2D and all 3D software methods to generate models, and investigate the use of 3D CAD modeling techniques. Okay. There are 2 assessments. The examination, which covers learning 1 and 2, and is of 2 hours. There's a slight caveat to that. The numerical methods in learning outcome 1 is included in the assignment because it's time consuming and not really easily assessed in the examination. When you come to do them, you'll kind of see why. All right. And then there's a portfolio which is like just a one-off submission assignment, but it's got 3 quite biggish tasks in it. Okay, covering, like I said, some of the numerical methods that we're evaluating, and also this use of software and 3D software to do engineering analysis. So that's covered in an assignment. Okay, 2 assessments are each worth 50%, so 50% the overall mark for the assignment, 50% of the overall mark for the examination. Yes, you've got to pass both. You've got to pass both assessments. In terms of examinations, from now, where it covers 2 learning outcomes, you haven't got to pass them both. You've got to just get 40% overall. So that's new. No, that's brand new, Lewis. All right, but you haven't got to do that anymore. All right. Right, so to that end, let's make a proper start. In your handouts that I've given you today, there's a couple of pages of drill questions, just to see how much you kind of already know around the topic today. All right, so there's a graph of a function there. Function of y is listed. What term would you use for the points A and B on the graph? What's the value of the slope at points A and B? Indicate on the graph a point where the slope is positive and another one where the slope is negative. How do we represent the slope in mathematical notation? And indicate the point that represents the root of this function. And then on the next page, a little bit of a drill around laws of indices, really, and how they work. In terms, we need that to be able to do our differentiation that we're going to look at today. So about 5 minutes or so, go see how much of that drill you can cover. Right guys, let's have a look at this. What term is used for the points A and B on the graph? A is A. Yeah, you could say if that was a graph of, you could argue that there's a point of inflection, I suppose. Not really, I would say no, not. Point of inflection goes like that. This one goes maximum and minimum, yeah. I'll just qualify that a little bit further and say it's a local maximum and B is a local minimum. Because in some functions, outside the range we're looking at, there could be other maximum and minimum values. Okay? But we're looking at quite a small range here of x values. Outside that range of x values, there might be, in some cases, in some functions, other maximum minima. What about the value of the slope of the graph at points A and B? Yep, the slope there is 0. Slope is represented by tangent to the graph at that point, and tangent to the graph at that point would be a horizontal line, and therefore the slope of that horizontal line is 0. And it's the same for point B too. So in calculus, come on Ben, sorry. Y is not changing at that point. Yeah. So there's techniques there's reason we can use differential calculus to determine where the maximum and minimum are in a function by the fact that we know that the slope is equal to 0 where there's a maximum and where there's a minimum. Alright, so we're going to be doing a little bit of that as we go through this module. Indicate on the graph where a point where the slope is positive and another where the slope is negative. So where's the slope positive on this graph? Anywhere on this left-hand side of A, we'd have a positive slope, and we'd have a positive slope there. Green, positive slope. Negative slope between A and B. Okay. What's the mathematical notation for representing the slope of that graph? Yeah, it's the slope represented by dy by dx in this case. Yep. There are other ways of writing it. In functional notation, we might use that for the first differential. So we might switch between those. But that represents the slope of that graph, dy by dx, mathematically. Okay, and then lastly, indicate a point on the graph that represents a root of this function. It's where, not quite, where it crosses the x-axis, yeah. It's the value, the root is the value of, and there may be more than one, value of x when y is 0 in this case. So that is a root. There could be other roots, positive and negative ones, okay? But that's an example of a root in terms of that one. And we can use various techniques to determine roots as well. Okay. Value of x to the power of 1. Sorry? X. Yeah. Any number to the power of 1 is that number. So you need to, the idea here is make sure you remember that you can write a plain x or any other variable as that variable to the power of 1 if it suits your needs. Yep. What's the square root of 9? What's the cubed root of 27? 3. Any number to the power of 0 is 1. Who said 0? Any number to the power of 0 is 1. Another useful, you can always write x to the 0 in front of something, and that x to 0 is equal to 1, so what you got there is still what you had in the first place. So you may need to remember that a number to the power of 0 is equal to 1. It's useful. Alright? How can we rewrite that in non-fraction form? Yeah, it's equal to 3x to the minus 3. The x and the power come on top, and we change the sign of the power. How can we write square root of x? And Dom, the last one? Anyone else? X to the 2 over 3. Yeah. And with that one, if you remember, it's the number outside that's the denominator, and the number, the index inside, that's the numerator. Then you won't go too far wrong. So you think about the square root one, which doesn't have an index inside, it's the 2 that goes underneath. Okay. So in terms of being able to do your differentiation in the rest of the session, you're going to need to be able to use these techniques to rewrite the function you've been given so that's in a suitable form for differentiation. So, you've got your laminated tables of derivatives that I've issued you this morning. I've also included the standard derivatives that we're going to use today in a table within the notes as well, so you've got them everywhere. So these are the functions that we're going to look at: ax to the n, e to the ax, ln ax, sin ax, and cos ax. We won't be using any others, as far as I can remember, throughout the module. Okay? So, let's have a look at a couple. Y equals 12x cubed. Which entry in the table are we to differentiate that function? Sorry? That's fine, but I want to know how you've done that, Seppi. Which? Yep, exactly. So you're using this entry from the table. Ax to the power of n an x to the power of n minus 1. Yep. So the process is we multiply by the index, so we do 3 times 12, put the x in, and take 1 off the index. And this is dy by dx is equal to 36 x squared. Okay. B, we've got y equal to 12 over x cubed. Lewis. Ben. What's that? Is that a minus? No, that's 2. Oh, this one? Now, if you take 1 off 3, you get 2 then. Yeah? Yep. Alright? So, Lewis, how do we rearrange that so we can differentiate it? Yeah, so dy by dx is equal to minus 3 times 12. So we multiply by the index, and then we take 1 off the index, x to the minus 4. So that's minus 36, x to the minus 4. Okay, how could we rewrite that in its original form? Sure? Yeah. Change the sign. Yeah. Those two answers are correct. And in an exam, you had one as simple as that you get full marks for either. Okay? So that's those two relatively easy examples. Okay? We're just refreshing what we did last year. So, a couple of special cases. Y is equal to 6. How could we rewrite that so we can see what happens when we differentiate a constant? How could I put an x term in there and still have y is equal to 6? Yeah, I can say that this is equal to 6x to the 0. Yep. Now what happens when we differentiate? What we got to do, Ben? What was the process we did before? Step by step. Anyone else? Process we did before, step by step. Multiply by the index. Take 1 off the index. What's nothing times 6x to the minus 1? Nothing times anything is nothing. i.e., when we differentiate, constants disappear. Okay? Remember that C having to come back, Dom, right? Okay, whatever it was. But that's the disappearing constant. All right? Yep. So, and secondly, on this page, B, y is equal to 6x. Can we write that? We can apply differentiation to it. Power of 1, yeah, because then x will still equal x, won't it? So I've just add a power of 1 on there. Then if we apply differentiation to that, dy by dx is equal to, we've got multiplied by the index, take 1 off, yeah, so it's 1 times 6 times 1 is 6. Yeah, so x terms, or any variable to the power of 1 term, you just end up with a constant. If you think about a function that has an x in its first term, like y is equal to 3x plus 2, that's a linear function, and the slope is a straight line, so the slope is a constant, doesn't change. Yep. Okay, so go through that process so that you can understand why constants disappear and single x terms, no power, you just leave the constant behind. Alright? Or the coefficient behind, I should say. So, problem 4. Differentiate that function. How do we go about doing that? Someone like to tell me what we need to do. We got y is equal to 5x to the 4 plus 4x plus 1 over 2x squared plus 1 over square root of x minus 3. Yes, shape each term, but there's something we need to do first. Sorry?
Between 4x and 1 over 2x.
Well spotted, my deliberate mistake. So we need to put those in non-fractional form. Yep. So we need to rewrite this as 5x to the 4 plus 4x minus, what have I got to put here? 2x to the minus 2 plus if I write, yeah, that would be x to the half. So therefore, I've got to write x to the minus a half. Yep. Okay. Now differentiate it. Give me all terms. Process here is 4 times 5 is 20. X, take 1 off the index, x to the 3. This, how we write this would be x to the 1. Therefore, that's going to be just plus 4. Yeah, constant. Minus 2 times minus 2 is plus 4. X to the minus 3 minus a half x to the minus 3 over 2, and then the constant on the end disappears. And that would be a more than adequate answer for an examination question. You don't need to put the fractional values back to get the full marks. All right? Happy with that, yeah? Comfortable. So, Find the differential coefficients of a y equals 3 sine 4x and b f of t, which is just another way of writing it, is equal to 2 cos 3t. So what's the entry in the table for a sine function? Sine AX, sorry. dy by dx equals a cos AX. So pulled from the table, they are the derivatives we need to use. So the answer for A is, Ben? Yep. So the 4 comes out times by 3, 12. So that inside the sine function stays there. Constant in front of it comes out. Okay. If I use the function notation f like this, how do I designate the first derivative? F with 1 dash t is equal to, Jack? Minus 6 sine 3t. You could do, yes, but if you, it depends on the application and the problem you're looking at. You may be using function notation. Okay, so they're just different ways of writing it. Yeah, I would suggest if the question is given you as a function notation, you'd write your derivative using function notation. If it's given to you as the top one, you'd use dy by dx or dy by dt or whatever the dependent variable. Okay, what we got for the first one then? The entry in the table is the second one down. So we got e to the ax is what we're using. So looking at the entry on the right hand side of the table, we've got to bring this constant 5 outside and multiply. So it's 3 times 5 is 15, and then e to the 5x. And that's something to remember with exponential. E to the power of function is that if we differentiate e to the power of x, we end up with e to the power of x. That's why it's special. Okay. What we got to do with this one so that we can differentiate it. Sorry? Yeah. You got to write it as, Dom? So f dash theta is equal to minus 6 e to the minus 3 theta. Yeah. Sepi, last one. Yep. Okay, entry in the table says if we have the function log of ln of ax, the result of that is 1 over x, and in this case we've got to multiply by the constant 6. Yep. It's like you're thinking of separating this function into the constant 6 and the function ln ax and doing them separately. Yep. Multiply by and so on. Okay. So they are the basic functions that we're going to use throughout this module. What we're now going to move on to are the formula for differential calculus, so that we can differentiate, first of all, a product of two functions, i.e. where u and v are two functions of x or some other variable multiplied by each other. There's a process to go through and a formula to use. The quotient rule, where u and v again are two separate functions, one divided by the other. And lastly, where you've got a function inside another function of a function. We use what's called the chain rule or function of function rule. So we're going to have a look at using each of those rules now, go through that process. Just remind you, should have all have done that before anyway, but just remind you of what the processes are, and then there's some practice questions for you to have a go at end of the session or at your leisure. So, product rule. I'm going to start off with the finding the differential coefficient of the function 3x squared times sine 2x. So that's a function of x, 3x squared. That's a function of x, sine 2x. But we can't differentiate them separately because they're not added to each other or one subtracted from the other. They're multiplied together. Okay, so we've got to use this process of using the product rule. Can anyone remember what that is from last year? Yeah, I usually split my board up, don't I? Sorry? Yeah, we're using the formula. Yeah, so we go let u equals 3x squared, and we let v equals sine 2x. For multiplication, it doesn't really matter which way round you put them, but for the quotient it does. So probably best to go in that order, u and v. Okay, then what we do is we differentiate u and we differentiate v. So differentiating u, dy by dx, not no, it's not. It's du by dx. Equals 6x, yeah. dv by du 2 cos 2x. No, you don't do that. You've got to use that formula, Lewis. Look at the formula for product rule in your here, product rule, right? It's a function times a function. Okay? So if you look at the formula, we've got to put now, bring all this together, dy by dx, this is by product rule, dy by dx equal to, and then there's u, so what do we call u? 3x squared. I tend to put all these in brackets to start with. We've got to multiply that by dv by dx, so that's your 2 cos 2x. And then we've got to add v sine 2x and multiply that by du by dx, which is 6x. So put all the values in the formula. Right, I'll write them what these are underneath. That is u. This is dv by dx. This is v, and this is du by dx. And there's a plus in there. Alright, and then finally we can write it out in nice neat form. dy by dx is equal to, sorry? Six x squared on yep plus 6x sine 2x. My little mistake, Seppi. Sorry? Yeah, you can. You can take 6x outside brackets. However, for those that want to be comfortable, I wouldn't necessarily expect you to do that in the exam unless I asked for it in its simplified and simplest form. Which I won't do. Essentially, you get the same marks for that or that in the exam question. Okay, because it's the fact that you can use the product rule that I would be testing, not that you can put it in any particular form. Okay? So, have a go at the problem 12 underneath, just quickly, 3 minutes. Right guys, what are we going to do with this? IT, du by dt, therefore v must be sine 2t is equal to cos. We end up with dv by dt. That's unfortunate, this function as v really, and but mind, is equal to multiply that by du cos 2t, and then that's plus sine 2t times we can write plus 5 2t. Can we go any further? You want make be 2t cos 2t plus sine 2t. What point? V equals 5 times 2 cos 2 times 0.2 plus sine 2 times 0.2. Okay. In yeah, this is the result you're looking for. That's the that is with 4 sine 5x divided by 5x to the 4. We need to use this quotient rule. In half 1 equal to 5x is sine 5x dv by Okay, then we've got dy by dx is equal to, and here to make sure you get them in the right order for the quotient rule. On the top, put v, which is 5x to the 4, times du by dx, 20 cos 5x. U dv by dx, which is 20 work on. As square 2 to the power 4 squared. So you the indices there x is equal to x to the a times try use the all time. Time in front. With what we called you in. So real crucial. No. And very much depends put in as to how well you do an exam.